Good afternoon, ladies and gentlemen. Today I want to introduce the summary of our paper, Faces in Event Streams, an Annotated Face Dataset for Events Cameras. My name is Tamiris Rahimjanova, and I'm a research assistant from the Institute of Smart Systems and Artificial Intelligence Laboratory. The new direction of the event-based camera in the field of computer vision is a growing topic of research in various fields. Beyond smart event cameras, a new type of vision device, and the main advantages of the event camera over conventional cameras is that such cameras read each pixel asynchronously, simulating the work of the human retina and detect only changes in brightness. Output represents a four-dimensional tuple XYPT, thus the output of such cameras consists of the information about the X and Y location of the pixel, the time when the event occurred, and information about the polarity value of 1 for the on events and 0 for the off events, depending on the brightness decrease and brightness increase. Event cameras offer significant advantages over traditional cameras such as ultra-low latency, no motion blur, low power usage, and high dynamic range. And on the right side of the presentation, you can see the RGB images, image-like visualized from the event stream's output, and gradient transformation from the event stream output. Face detection is artificial intelligence-based computer technology used to find and identify human faces in digital images. Face detection is the first and essential step for face recognition, and it is used to detect faces in the images. It is part of object detection and can use in many areas such as face recognition, robotics, emotional inference, industrial health, security, social media, and facial motion capture. Also, with the face detection, it is possible to improve the accuracy of the facial analysis by identifying the sections of a video or parts of a picture that should be focused on when determining specialties like gender, age, and emotions. Facial landmark detection is a computer vision task in which a model needs to predict key points representing regions or landmarks on a human face, eyes, nose, lips, and others. Due to the relatively recent introduction of the camera to the market, and also despite the existing research on face detection using the event camera, there is still no large dataset with the face and facial landmarks annotations on event streams that will give a boost to the development of camera applications in this direction. And here we showed the two to the best of our knowledge, the two datasets. The first dataset is the face pose alignments, and the next dataset is from the paper lens et al. And here we can see that there is a small number of participants and also the small duration. And also there is no bounding box annotations. And the last, it is our dataset FES. Those in this work will address this issue by publishing the first large and varied FES dataset face and facial landmark detection for a direct event camera-based output. Our main contribution consists: we release an open-source large-scale event-based FES dataset, 689 minutes of recorded of event streams captured at different lighting conditions from different viewpoints and distances, with multiple people in the skin and a greater number 73 and diversity of participants. Dataset is fully and accurately labeled with bounding boxes of faces and 5-point facial landmarks, eye centers, nose tip, and mouth corners. We introduced a dedicated deep learning model for face detection and facial landmarks detection. The model adapted from the paper Perez et al. Uses a hybrid architecture combining convolutional and recurrent layers. Our model is the first deep learning model making use of recurrent layers for face detection from event streams. Here in the slide, we can see the information about our faces in event stream dataset. And here we can see that the dataset consists of two major parts: controlled laboratory and uncontrolled wild environments. And also here we can see that 31 female and 42 male participated in the data collection experiments. And also a special attention was paid to the diversity of the participants, inclusion of different ethnicities and persons with the facial accessories. The data collection in the controlled experiments was conducted in indoor environment under bright and dim lighting conditions and also different distances from the camera, 50, 150, and 400 centimeters, and with the camera either moving and stationary. Head postures and movements included left, right, up, down, circle movements of the head and counting, whereas walking patterns consist of zigzag walking, walking towards the camera, and sideways walking. For each subject, 60 recordings were obtained. Uncontrolled data were also collected in indoor environments, corridors, coffee shop, classroom in the university campus, and also during these experiments, groups consisting of different number of subjects were asked to move freely in the field of the view of the event camera. Since there were no specific instructions on the movements and hand postures, subjects were casually behaving during recording, and also wore different accessories such as hat, mask, or glasses. Here in the slide, we can see the faces in event stream dataset video examples. As we can see in the slide, here's the provided information about the dataset annotation and visualization. And here we can see that for the annotation, an image-like visualization of event streams is obtained by accumulating events over short periods of time. The accumulation time is equal to the 33 milliseconds. Event streams were rendered by defining on events as a white pixel and off events as a black pixel and backgrounds as a gray. Grayscale images obtained using MetaVision software. The annotation was done by SI laboratory moderators using CVAT annotation tool. And here we can see on the right side, here we can see the example of the image-like visualization of event streams and bounding box and facial landmarks annotation. As we can see in the slide, here's the provided information about the deep learning model architecture which we used in the paper. And our model is based on the model and learning to detect objects with 1 megapixel event camera paper, which was used for object detection in event streams. In this model, the researchers introduced a mechanism in which learning occurs through incoming events accumulated over periods and the use of prior information from the past events. So here we can see that the event stream is represented as a sequence of events, and the events is accumulated over a short period of time, named accumulation time. And after that, this accumulation time is transformed into tensor map using the histogram preprocessing function. Afterward, features are extracted from the tensor map, and we use the original feature extractor like in the paper, this was an excite block, and also the original feature extractor in our model was changed to the ResNet 18, ResNet 34, and ResNet 50 variants for the comparison. The key advantages of these networks is the use of the residual block, which connects two convolutional layers with a skip connection. Therefore, the output of the feature extractor was connected to the 5-layer convolutional LSTM that obtains an internal state information in addition to the extracted features. Finally, the output of each convolutional LSTM is fed into a two-head regression predictor, which consists of convolutional layers to predict face detection bounding boxes and 5-point facial landmarks. To validate the efficiency of our dataset, we trained 6 models for detecting only bounding boxes and 6 models for detecting facial landmarks and coordinates of bounding boxes at the same time. We use the average precision metric to validate the model, setting the intersection of a unit threshold to 0.5. And also we calculated normalized mean error to assess the performance of models to predict facial landmarks. The results are shown in the table. And here we can see the MIP mean average precision result for face bounding box detection. We can infer several conclusions from the results. The best mean average precision results were obtained using a model trained on event streams with an accumulation time of 50 milliseconds. Presumably, the accumulation time of 33 milliseconds was not long enough to collect a sufficient number of events for face detection, and similarly, the longer 100 millisecond accumulation time might have too many events on the face region, creating an equivalent of the blur effect in the visual images for the event stream. In general, the MIP score was higher for large faces, showing the difficulty of detecting faces farther from the camera. Also, compared to the laboratory testing set result, the result for the wild part of the dataset received a lower score. This might be caused by the presence of multiple faces on event streams in uncontrolled poses. The best results for the face bounding box detection were achieved by the model with the ResNet 18 feature extractor and 50 millisecond accumulation time. Among the combined facial landmarks and bounding box detection models, the best overall results were achieved using the model with the original feature extractor and the 50 millisecond accumulation time. The lowest NME score on the overall testing set was obtained using the model with 100 millisecond accumulation time and the regional feature extractor. Also, among models with a 50 millisecond accumulation time, the model with ResNet34 feature extractor and the model with the original feature extractor with over 50 millisecond time have the similar NME scores. However, the lowest NME scores on the overall testing set obtained using the original feature extractor by a small margin. Here we can see the references which are used in my presentation. Here we can see the demo video of using the our models in real-time detection. So thank you for your attention. Goodbye.